Let us understand refraction at spherical surfaces. We have so far considered refraction through a plane interface. We shall now consider refraction through a spherical interface between two transparent media. An infinitesimal part of a spherical surface can be regarded as planar, and the same laws of refraction can be applied at every point on the surface. That is, angle of incidence equals the angle of reflection. And incident ray, reflected ray, and normal lie in a plane. Just as for reflection by a spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane to the spherical surface at that point and therefore passes through its center of curvature. Consider a spherical surface with center of curvature C, radius of curvature R, and refractive index N2. The rays from O are incident from a medium of refractive index N1 to another medium of refractive index N2. The rays after incidence forms image at I, where I is the angle of incidence and R is the angle of refraction. The aperture of the spherical surface is taken very small as compared to the distance travelled. Hence, a small angle approximation can be made and nm can be taken to be nearly equal to the length of the perpendicular from the point N on the principal axis. Now, for small angles, we have tan of angle NOM equals Mn by Mo and tan of angle NCM equals Mn by Mc. Similarly, tan of angle NIM equals Mn by Mi. Now for triangle NOC, I is the exterior angle. Therefore, I equals angle NOM plus angle NCM. This implies I equals Mn by Mo plus Mn by Mc. Similarly, angle R equals angle NCM minus angle NIM. That is, R equals Mn by Mc minus Mn by Ni. Now, by Snell's law, N1 sin I equals N2 sin R. For very small angles, sin I equals I and sin R equals R. Thus, N1I equals N2R. After substituting value of R and I, we get N1 into Mn by Om plus Mn by Mc equals N2 into Mn by Mc minus Mn by Mi. On further simplifying, we get N1 by Om plus N2 by Mi equals N1 minus N2 by Mc. Now, apply the Cartesian sign convention. Om equals minus u, negative because distance is measured in the direction opposite to the direction of light. Mi equals plus v and similarly Mc equals plus r. Substituting these in equations, we get N2 by v minus N1 by u equals N2 minus N1 by r. This equation gives us a relation between object and image distance in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. It holds for any curved spherical surface. The following diagram shows the geometry of image formation by a double convex lens. U equals the distance of the object from the optical center. V equals the distance between optical center and final image. The image formation can be seen in terms of two steps. The first refracting surface forms the image I1 of the object O. The image I1 acts as a virtual object for the second surface that forms the image at I. Applying the equation N2 by V minus N1 by U equals N2 minus N1 by R to the first interface ABC, we get N1 by OB plus N2 by BI1 equals N2 minus N1 by BC1. A similar process can also be applied to the second interface. That is, ADC gives, we will get minus N2 by DI1 plus N1 by DI equals N2 minus N1 by DC2. DI1 is negative as the distance is measured against the direction of incident light. For a thin lens, BI1 equals DI1. Adding equation 1 and 2, we get N1 by OB plus N1 by DI equals N2 minus N1 whole into 1 by BC1 minus 1 by DC2. Suppose the object is at infinity, that is, OB tends to infinity. Then the point where image of an object placed at infinity is formed is called the focus F of the lens, and the distance F gives its focal length. A lens has two foci, F prime and F, on either side of it. Suppose the object is at infinity, that is, OB tends to infinity. Then the image of the object at infinity falls at the focus DI tending to F. N1 by infinity plus N1 by F equals N2 minus N1 into 1 by BC1 minus 1 by DC2. This implies N1 by F equals N1 whole into N2 by N1 minus N1 into 1 by BC1 minus 1 by DC2, where N2 by N1 equals N21. This implies 1 by F equals N21 minus 1 into 1 by BC1 minus 1 by DC2. Since BC1 equals R1 and DC2 equals R2, we have 1 by F equals N2 minus N1 by N1 into 1 by R1 minus 1 by R2. This equation is known as the lens maker's formula. This formula is true for a concave lens also. In that case, according to sign convention, R1 is negative, R2 is positive, and therefore F is negative. From the equation, N1 by OB plus N1 by DI equals N2 minus N1 1 by BC1 plus 1 by DC2. This implies N1 by F equals N2 minus N1 into 1 by BC1 plus 1 by DC2. This implies N1 by OB plus N1 by DI equals N1 by F. Again, for the thin lens, OB is minus U and DI is plus V. Then the equation will become 1 by V minus 1 by U is equal to N1 by F. This is the thin lens formula. This is valid for both convex as well as concave lenses and for both real and virtual images. How to find the image of an object by a lens? Take any two rays emanating from a point on an object. Trace their path using laws of refraction and find the point where refracted rays meet or appear to meet. However, it is convenient to choose any two of the following rays. A ray emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus f prime in a convex lens or appears to diverge in a concave lens from the first principal focus f. We can also take a ray of light passing through the optical center of the lens emerges without any deviation after refraction. A ray of light passing through the first principal focus for a convex lens or appearing to meet at it for a concave lens emerges parallel to the principal axis after refraction. This ray of light can also be taken for the image formation. Now join the two ray diagrams and make them like this. You will find the required image of the object. Let us study about magnification M. Magnification M produced by a lens is defined similar to that of a mirror, that is, the ratio of the size of the image to that of the object. In mathematical form, it can be represented as M equals h prime by h, where h prime is the height of image and h is the height of object. Therefore, M can be written as O prime Q prime divided by OQ. From triangle OQP and triangle O prime Q prime P, we have O prime Q prime equals PO prime divided by PO. But since PO prime equals minus U and PO equals minus V, we have M equals minus U by minus V, or M equals U by V. Since proper sign conventions are used, the above equation is valid in all situations with a single thin lens.